Hi everyone, I'm Myles Foley. I'm a PhD student at Imperial College London. I'd like to thank my co-authors Salim Wahaibi and Sergio Maffeis. And this, in about 12 minutes or less, is SQIRL grey box detection of SQL injection vulnerabilities using reinforcement learning. So quick recap on SQL injection. I'm sure you're probably already vaguely familiar with it. SQL injection is present when a user inputs some kind of input into a web form or something on a web page, which then gets executed in an SQL query. This is all fine, except when nefarious users try to input some SQL to get some additional functionality out of the database. This could be extraction, manipulation, or something nice and chill here, which is causing a sleep. Now, don't worry, don't panic. We can defend against this. Certain things like user input sanitization is very commonly used either in whitelisting or blacklisting. The only slight problem with that is that it's very dependent on how developers implement it, so there can still be vulnerabilities. The more standard way of defending against this is through the use of prepared statements. So we've got an example here, which is from WordPress, a current example. And in prepared statements, you bind parameters to specific types to render them benign, as you can see with the meta key here. However, you may notice that the ID column is also, or is not in the prepared statement, bound correctly, so it could still be vulnerable to SQL injection if a user input is unsanitized and fed into that. So we kind of see that some defenses are pretty diverse. So what we probably need is payloads that are equally diverse so that we can try and find these vulnerabilities. So you see here, this is 1,028 payloads that are taken from existing words lists and from current scanners. And we performed a feature reduction to have a bit of a visualization about what these payloads look like. And you see that they're all very densely clustered together, and there's a lot of sparsity in this space. Now, I'm not saying that all the points within this payload space could lead to legitimate vulnerabilities or even legitimate payloads. Merely that potentially we might want to explore this extra space to try and find some vulnerabilities. So what do existing tools do? Tools like Arachne and Wapiti tend to use a smaller number of payloads in a payload list, offering very little or no mutation strategy, and they don't really attempt to bypass any sanitization. The gold standard for this is kind of SQL map, which if you're familiar with SQL injection, you will have used SQL map, but it predominantly focuses on functionality, offering a pretty good rule-based strategy for generating payloads, but minimal anti-sanitization, generally looking at PHP. So this is where we come in. So we introduce a deep reinforcement learning-based gray box detection of SQL injection. There's a lot going on here. Don't worry, we're going to break it down. So we cast the SQL injection problem in the RL paradigm. So an agent is able to take actions, AT, which are turned into concrete mutations on a payload, which is generated from scratch. The payload control module then takes this payload, casts it into a HTTP request, sends that to the web application, that executes the query into the database. We're Greybox, so we hook into the log files from the SQL database to extract the SQL statement. And this is quite useful because we use this for our state representation. So this is what the agent will observe in order to decide which actions to take. So the state we choose is based off of the SQL statement that's been executed, the payload that we generated, and a single bit to represent if there's a syntax error in the SQL statement. We can also then use a reward as well to determine how good this state is, and this is what the RL agent is going to try and optimize for over training. So how do we do this? Well, we play a number of games. We start with the context escape game. So whenever we start trying to find a new vulnerability, we try to generate a syntactically correct payload that breaks out of the initial context within the SQL statement. So single quote, double quote, things like this. If we're able to do that, we then try to change the behavior of the SQL statement that's being executed. Don't worry, we're not going to drop tables, we're not going to steal your data. We're just going to execute a little sleep statement to demonstrate that a vulnerability could be present. Now, God forbid that the web application actually tries to defend itself and do some kind of sanitization. If it does, don't worry, we're prepared for it, and we are able to enter the third game, which is sanitization escape. So we try to replace anything within the payload with a semantic equivalent if a sanitization is detected on the SQL statement. So for each of these games, we cast the actions separately and unique to each game. So each game has separate sets of actions. So for instance, in the context escape and behavior changing, we have tokens that can be input into the payload or removed from the payload at any point during the payload. So this becomes a like diverse and growing set of actions that we can do to generate unique and diverse payloads. We're also then able to replace semantic equivalents within the payload as well, as you can kind of see on screen. I won't list off all 23 actions because I think you might get a little bit bored, and I might do too. So we're able to transition between each of these games more or less as I've just described using this transition function. But this also does something pretty useful as well. It defines our reward. So we use a very traditional sparse reward in reinforcement learning, but we flip it on its head a little bit. So instead of rewarding for good behavior, we just penalize for bad behavior to try and incentivize and motivate as quickly as possible to try and find these vulnerabilities. So our agent architecture is based on the deep reinforcement learning deep Q network, which usually off the shelf will take in a fixed length input and a fixed length output. So there's a bit of a problem here based on how we've set up the problem, because SQL statements and payloads are of, well, they're strings and they are of non-fixed length. So what we do to get around this is we define two autoencoders to create like an embedding representation of like a float vector for each of the SQL statements and the payloads. This is then combined with the error bit to form the state representation. So these autoencoders are based off of recurrent neural networks, so we feed each of these strings in token by token to get a representation. Now, there's also the other slight problem that I mentioned where actions are growing and changing as we build our new payloads. And in normal reinforcement learning, you have a fixed length output, which is the number of actions that you have, but we have a growing and changing number of actions. So what we do is we tell the agent, okay, this is the state that you're currently in, this is the action that you can take, and give us the value of this action. And we do this for all possible actions at every time step. So you may have also seen as well in here that we have local workers. So what this means is we use a number of workers to try and collect diverse experiences by interacting with the payload, with its instance of a payload control module, to try and collect these diverse experiences in parallel to bootstrap and improve the stabilization of learning. These are then like experiences are aggregated in the global agent via neural network averaging of the weights, and then passed back to the local agents. And this in training, I think we use 4 of these. So yeah, training as well. We develop a new microbenchmark, which contains 30 vulnerabilities. We use 20 for training. We use another 10 just for testing, including 5 CVEs. There's a bunch of sanitizations that go on there, a bunch of different contexts, SQL statements. Again, I'm not going to read these all to you because you might get bored, and I might do too. So how does it do in evaluation? So we compare on our microbenchmark and against a number of scanners. We provide them for certain tools with feedback on the query or feedback on the exception if one is caused in the web page. And we see that, so as well, yeah, green is good, red is bad. SQIRL, the reinforcement learning agent, is able to find more vulnerabilities than most other scanners, except for one of them when it has an exception feedback in the page, which generally speaking you don't want in production. We're able to do so in fewer requests. Again, there's one caveat there. There's one tool that's able to find it, use less requests, but it finds less vulnerabilities as well. But we're also able to do this with no false positives. But this is all like very lab-based, so how does it do in the wild? We pick 4 web applications that have CVEs from the last year from manual testing, and we throw all the tools at it and we see how it does. We're able to see that SQIRL finds more vulnerabilities than any of the other tools. It's able to, interestingly, find 6 new CVEs that were missed from manual testing, and we're able to do so in a lower number of requests than our random counterpart, showing the like intelligent nature of the reinforcement learning agent. And importantly, we're able to do so in competitive time, so that when used by normal people, we can actually use this efficiently, even though we're using a deep learning architecture. We do a little bit of a study on how worker agent configurations affect performance in the number of workers that we have and in the distribution of what they're trained up against. We also do an ablation study to demonstrate the design choices, but I will refer you to the main paper for details on that. But suffice to say, the design choices we make do improve performance. Finally, we manually analyze all of the payloads that each scanner is able to produce. We see that SQIRL produces the most payload types. It produces 10. And it's also able to use more features in the payloads that it is able to produce, as you can see with the ticks on there. So yeah, to conclude, we've developed a gray box reinforcement learning SQL injection scanner, SQIRL, which found more SQL injections in our microbenchmark and on production-grade web applications at 63. This is more than any of the other scanners. It was able to find 6 new CVEs, and this is thanks to the diverse payloads that it's able to generate with its diverse features. So with that, I'll thank you for listening, and if anyone has any questions, I'm happy to answer them.